Hello students, I am Sachitrakar. Welcome to Cars Physics. In this lecture, we will discuss a beautiful concept on work. Okay. In previous lectures, we have discussed the fundamental definition of work and different types of work. For example, positive work, negative work, maximum work, minimum work, and no work or zero work. Okay. And we have done some fundamental numericals on the basis of formula. Okay. In this lecture, we will discuss work done by conservative force and work done by non-conservative force. Work done by conservative force and work done by non-conservative force. Okay. Let's first understand what is the concept of work done by conservative force and non-conservative force. Okay. Then we will go to conditions, means mathematical conditions for conservative force and vice versa is for non-conservative force. Okay. And those conditions are very important to check whether the force is conservative or the force is non-conservative. Okay. And we will have some basic questions or numericals on the basis of these two concepts, work done by conservative force and work done by non-conservative force. Okay. Work done by conservative force and work done by non-conservative force. Number one, work done by conservative force. Work done by conservative force is independent of path or independent of path length. Okay, but depends upon initial, depends upon only on initial and final position. Okay, so work done by conservative force is independent of path or independent of path length, but depends upon only on initial and final position. So what about non-conservative force? This is point 1, this is point 1. Work done by non-conservative force is path dependent. Beautiful comparison. Work done by conservative force is independent of path length, but work done by non-conservative force depends upon path length. Means if path length is more, then work done by non-conservative force is more and vice versa. Okay. But here, work done by conservative force is independent of path length, whatever be the path length. It only depends upon initial and final position. Okay. Second point, work done by conservative force in a complete path or closed path, same thing, closed path is 0. Work done by conservative force in a complete path or closed path is 0. It means if displacement is 0, complete path means the initial and final positions coincide. Where there is initial point, there is final point. Means the body starts from initial position and again comes back to initial position. Means both initial and final positions same. So if work is done by conservative force, then work done is 0. So work done in a complete path or closed path is 0. It means if displacement is 0, if initial and final point same, then there is no displacement. Means if displacement is 0, then work is 0. If work is done by conservative force. But here, number 2, in a complete path, or closed path is not 0. So work done by non-conservative force in a complete path or closed path is not 0. It means if work is done by non-conservative force, though displacement is 0, closed path means displacement is 0. If displacement is 0, then work done by non-conservative force is not 0. Here work is 0, but here work done by non-conservative force is 0. Sorry, not 0. Third point. Work done by conservative force defines change in potential energy. Work done by conservative force defines change in potential energy. It means to express change in potential energy, we have to take help of work done by conservative force. Means non-conservative force can't define the change in potential energy. Okay? But work done by conservative force defines the change in potential energy, and similarly here, work done by non-conservative force defines change in kinetic energy. Defines change in kinetic energy. Work done by conservative force defines change in potential energy, delta E, and this is delta E. Change in kinetic energy. This is change in potential energy. Okay? We'll explain all these points by taking examples. And these two concepts will come when we will discuss potential energy and when we will consider or discuss kinetic energy. Okay? Then some examples of conservative force. Best example in 11th is gravitational force. Then elastic force. And we have already discussed under variable work, spring force. Work done by spring force or spring force. F is equal to minus kx, spring force, x is variable, so spring force is variable. That's also conservative force. And finally, in 12th physics, you will go through electrostatic force. We'll take examples of conservative force in today's class, taking gravitational force. Work done by gravitational force. Gravitational force is conservative force, and similarly, here, example of non-conservative force, the best example which we'll discuss today itself. So, example is frictional force. You know friction, okay? Frictional force. When a body moves on a surface, then kinetic friction opposes the relative motion between the surfaces. And another example you may cite, that is tension. Frictional force, tension, etc. So we'll analyze all these points now. Have you taken all these points? Okay. Then some examples. See, first we will discuss that work done by conservative force is independent of path length but depends upon initial and final position. Very simple example. Let a particle moves from A to B. So A is initial position and B is final position. Let the particle moves from A to B in the shortest path. So this is path length. And the particle may move in a semicircular path from A to B, or it may move in any irregular path like this. Whatever be the path, this is path 1, this is path 2, this is path 3, and this is path 4. So work done by conservative force is independent of path length but depends upon only on initial and final position. Okay. Thus in this case, work done by conservative force in path 1 is same as that of work done in path 2, work done by conservative force in path 1 W1, in path 2 W2, in path 3 W3, and in path 4 W4. So whatever be the path, work will remain same because work done by conservative force depends upon only initial and final position. So whatever be the path length, work will remain same. But for non-conservative force, work done along path 1 is not equals to work done in path 2, not equals to work done in path 3, and not equals to work done in path 4. So if force is a non-conservative, then work done by non-conservative force depends upon path length. As you see, this path length is maximum. So work done along path 4 is maximum. Okay. And this is the shortest path. Work done by non-conservative force in the shortest path is minimum. Okay. So work done by non-conservative force depends upon path length. If path length is more, then work done by non-conservative force is more. Is it clear? Is it clear to you all? Okay. The next discussion. Work done in a complete path is 0. Work done in a complete path is 0 if force is conservative. Means work done by conservative force in a complete path is 0. Okay. We are taking example of conservative force here, gravitational force. Okay. Let's consider the surface of a tabletop. Surface of tabletop. Okay. And tabletop is horizontal. Tabletop is horizontal. Tabletop is like this. This is a horizontal surface. So tabletop is horizontal. So this surface, this is horizontal surface. Okay. Suppose a particle is at A, it is moved to position B, then it is moved to position C, then it is moved to position D, then it is returns back to position A. Then work done by conservative force, work done by conservative force, in a complete path, work from A to B, then from B to C, then from C to D, then from D to A. A to B, B to C, C to D, D to A. Then path is completed. Then as we know, work done in a complete path by conservative force is 0. How? See, suppose a particle is initially at this position, then weight of the particle is in vertically downward direction, and which is gravitational force. Force due to gravity, weight in vertically downward direction, and displacement along AB. AB is horizontal. AB is on the surface. This is weight, and this is direction of AB. And in this case, from A to B, angle between force and displacement is 90 degrees. Gravitational force or force due to gravity in vertically downward direction, and AB is on horizontal surface. Okay. Then here, to move the particle from B to C, again, weight is in vertically downward direction and displacement is on horizontal plane from B to C. So here also theta is, from B to C, theta is also 90 degrees, and from C to D, again, this is direction of weight, direction of displacement from C to D along horizontal surface, and this is direction of weight. Here also theta is 90. Then from D to A, here weight or gravitational force is mg, and displacement is perpendicular to the direction of gravitational force. Here also theta is 90. As we know, if angle between force and displacement, this is force, this is displacement. So this is force, this is displacement. This is force, this is on horizontal plane, this is displacement from C to D and from D to A also. In each case, theta is 90 degrees. And as we know, if angle between force and displacement is 90 degrees, then there is no work. Work done is zero. Okay. So total work from A to B, from B to C, from C to D, and from D to A, total work is zero. Work done by conservative force in a complete path is zero, because in each case, for each part of this path A, B, C, D, force and displacement are mutually perpendicular to each other. So it satisfies the condition for no work. The total work is zero. But if the force were non-conservative, if frictional force is taken into account, then work done by frictional force is equal to change in kinetic energy. Work will not be zero, but work will be equals to change in kinetic energy. Okay. Here work is zero. So change in potential energy also zero. We'll discuss it. Potential energy. Okay. Next, some other discussion. Work done by conservative force. Okay. Let's consider this is an inclined plane. This is horizontal surface. This is inclined plane. Let this angle is 90 degree and the angle of inclination is theta. This path is length L and this is height h. This is length x. Okay. Let's consider a particle of mass m moved from A to C. So this is path 1. Then the particle is taken first from A to B, then from B to C. This is path 2. So here, work done in path 1, work from A to C. Here, work done from first A to B, then from B to C. From A to B, then from B to C. So work done by conservative force is independent of path length. But here, in path 2, path length is more. In path 1, path length is less. We have to prove that. Work done by conservative force is independent of path length, but depends upon initial position. Initial position is A and C is final position. A is initial position and C is final position. This is path 1, this is path 2. We have to prove that work is same. In path 1, work done from A to C, initial and final position C. If mass of the body is m and the position is A and angle of inclination is theta, then component of force due to gravity or gravitational force parallel to the plane in downward direction is mg sin theta. Just recall. You place a body here, weight acts in vertically downward direction, this angle is theta. This is perpendicular to plane, so this angle is theta, this component is mg cos theta, and parallel to the plane the component is mg sin theta. Thus mg sin theta acts parallel to the plane but in downward direction, and displacement is from A to C. Here displacement is L from A to C. So what is angle between them? Mg sin theta and displacement are in opposite direction. Displacement from A to C, mg sin theta is opposite in direction. So as you know, here theta is equal to 180 degree. Force and displacement are in opposite direction. Theta is 180 degree. So work from A to C is Fs cos 180. That's equals to minus Fs. So here force is mg sin theta minus mg sin theta, and displacement is from A to C. Magnitude of displacement or path length is L, so mg sin theta into L, and finally we will get minus mgl sin theta. Work is done against force due to gravity. Force due to gravity and displacement in upward direction. Okay. Means work done by conservative force. Okay, then path 2. Path 2 means work done from A to B, then from B to C. Let's first find work done from A to B. A to B. See, if the body is taken from A to B in the sin theta, from A to B, this position is position A, this is B. Work from A to B. See here, force due to gravity mg in vertically downward direction, and x means displacement perpendicular to the direction of force. So here theta is equal to 90 degree. Angle between force and displacement is 90 degree. So work from A to B is equal to Fs cos 90. That's equals to 0. Means mg x cos 90. Force is mg, displacement is x, and theta is 90, work is 0. Then work from B to C. Work from B to C. Now let's place the particle at position B. Then gravitational force or force due to gravity acts in vertically downward direction, mg, and displacement is in upward direction. So angle between them is 180 degree. So here theta is equal to 180. So force is mg, displacement is h. Both are in opposite direction. So as we know, work from B to C is equal to Fs cos 180. That's equals to minus Fs. Here force is mg, displacement is h, minus mgh. But you see, if you consider a right angle triangle, this angle is theta, this angle is 90, this perpendicular is h, and hypotenuse is L, then sin theta is equal to perpendicular h upon hypotenuse L. Then h is equal to L sin theta. Very easy. So now put L sin theta. Then work done from B to C is equal to minus mg. In place of h we will write L sin theta. Then total work done from A to B, then from B to C is equal to Work done from A to B is 0, is 0, 0 plus. Work done from B to C is minus mgl sin theta. Then total work is minus mgl sin theta. So in path 2, work done is minus mgl sin theta. In path 1 also work is minus mgl sin theta. So work done by conservative force is independent of path. For path 1 and for path 2, work is same. So work is independent of path. Is it clear? Is it clear to all? Okay. Then now the time to know the conditions which must be satisfied so that the force is conserved. So if an equation is given to you, means equation for force, then you can check the force is conservative or not. Is it clear? Okay. Suppose we are expressing force in terms of its rectangular components. We are expressing force in terms of rectangular component. Okay. Then force in terms of rectangular component is given as Fxi cap plus Fy j cap plus Fz k cap. Force in terms of rectangular components of force are Fx, Fy and Fz are directed along x-axis, y-axis and z-axis respectively. Okay. Then conditions for conservative force. Conditions for conservative force. See, the first condition, we have to take the derivative of component of force, means rectangular component of force, d by dy of a component of force along x-axis must be equals to d by dx of component of force along y-axis. This is partial derivative, means while taking differentiation of fx, the y and z components are 0. Only we have to take x. Okay. So y and z components are treated as constant. Only x component is variable. Okay. Similarly, again partial derivative. This is just see. This is x-axis. This is y-axis. And this is z-axis. This is the origin left. This is our required force. This force has component Fx along x-axis, Fy along y-axis, Fz along z-axis. Okay. Now this is about x-axis and y-axis, Fx and Fy. And similarly, we may take for y-axis, z-axis, the components are Fy and Fz. d by dz of Fy must be equals to d by dy of Fz. Second condition, z and y axis. Then x axis and z axis. Third condition, d by dx of component of force along z axis must be equals to d by dz of component of force along x axis. Okay. These three are required conditions for conservative force. If these conditions are satisfied, then force is conservative. If these conditions are not satisfied, then force is non-conservative. Keep it. Have you taken this? Okay. These are conditions for conservative force. Now we will have some discussion. Means example or discussions. Keep it in your mind. This is very important to check whether the force is conservative or not. Okay. dfx by dy is equal to dfy by dx, dfy by dz is equal to dfz by dy, dfz by dx is equal to dfx by dz. Partial derivative. Very simple. Okay. Then some example discussion on the basis of these conditions. Okay. Number one. Suppose a force is given like this. Expression of force given like this. Suppose force is given 2y I cap plus 2x j. So you have to determine whether the force is conservative or non-conservative. Step. The force F is conservative or non-conservative. Or you may face it in objective base also, on the basis of work. Some closed path will be given to you. Then you have to state whether work done is 0 or not. Okay. So, this is 2y, x component fx, fx I cap, fx is 2y, fy j cap, magnitude of fy is 2x, but magnitude of fz is not given. So, component is 0 along z axis. Okay. Then, only condition on x axis and y axis, we have to prove it, means dfx by dy is equal to, let's find it first, is equal to d by dy of fx component of force along x axis is 2y, means 2y. 2 is constant, bring it outside, then d by dy of y is 1, then result is 2. Similarly, d by dx of fy, that's equals to d by dx component of force along y axis is 2x. In place of fy you have got 2x, then d by dx of 2x, again 2 is constant, bring it outside, d by dx of x is 1. So 2 is equal to, means dfx by dy is equal to dfy by dx. We have proved values are same. So the force is conservative. Here z axis, the component along z axis is not given. So only to check the component of force in x axis and y axis. The only condition. If it is satisfied, then the force is conservative. Clear? Suppose a force F, I am changing the expression, a force F, F is equal to 3x I cap plus z displaces a particle from along O to A, A to B, B to O, as so on. I am showing on xy plane. This is along x axis, this is along y axis. 3x I cap 1 j cap, means here z component is 0, so 0 k. So that I am taking xy plane. A particle of mass m is displaced from O to A, then from A to B, then from B to O. Okay. Suppose coordinates are also given. This is origin, coordinates are 0, 0. Coordinates of point A are A and A, and coordinates of point B are 2A and B. Accordingly, we can calculate the angle also, theta 1 and theta 2, but let's first check if the force is conservative or not. If the force is conservative, then OABO, OABO, O to A to B, B to A, then path is closed, a complete path. Then if the condition is satisfied and it can be proved that the force is conservative, then obviously work done in this complete path is 0. No need to calculate theta 1, theta 2, mg theta 1, mg theta 2. Okay, and here mg into angle, no need to calculate. Just let's see that the condition for conservative force is satisfied or not. The force is given, means component of force are along x-axis and y-axis. Here Fx is equal to 3x, Fx I cap, 3x I cap, and magnitude of F1, Fy is a cap, 1 into j cap, magnitude is 1. Then only condition. Let's find dFx by dy. So d by dy of 3x. d by dx of 3x. See, 3 is constant. Fx is 3x. 3 is constant. Again, x is constant because we are taking partial derivative. So 3x is constant with respect to y. 3x is constant, so differentiation is 0. Similarly, differentiation of dfy, partial derivative with respect to x, that's equals to d by dx of fy is 1. Again, it is constant 0. So 0 is equal to 0. So d by dy of fx is equal to dy dx of fy, 0 and 0. So the condition for conservative force is proved. If these two are same, then force is conservative, and in this case total work from O to A, from A to B, from B to O is equal to 0. Because force is conservative, no need to calculate. Okay. Then some examples of non-conservative force. Okay, very easier discussion. Very easy discussion. And as I have discussed, the best example for your discussion, best example of non-conservative force is frictional force. Okay. Let's consider this is a horizontal surface. A body of mass m is taken from position A to position B, and then it is brought from position B to position A. I am showing in different diagram. This is position A. This is the body of mass M. It is moved from A to B. First it is moved from A to B, then it returns from B to C. This is direction of motion. Let displacement from A to B is S. Okay. When the body moves from A to B, then kinetic friction opposes its motion. So here displacement is from A to B, and kinetic friction is directed opposite to the direction of motion, means from B to A. So here theta is equal to 180 degrees. So work is equal to Fk, force, displacement is S cos 180 degrees, that's equals to minus Fk into S. So negative work is done. And similarly, if you take the body is brought from B to A, again displacement is S. When the body moves from A to B to A, then kinetic friction opposes its motion. Here also. Theta is equal to 180 degree, and work. This is from A to B. This is from B. Here also work is equal to kinetic friction, displacement, cos theta, cos 180, and that's equals to minus Fks and total work. As work is scalar quantity, total work means work done from A to B, then from B to A. Work done from A to B is minus Fks plus work done from B to A, again kinetic friction and displacement, magnitude of displacement, then the result is, which is not zero. The path is completed from A to B, then from B to A. The body starts from A and returns back to A. Means path is closed. Then work is zero if the force were conservative, but here we have taken frictional force. The force is non-conservative, so work is not zero. Work is not zero. Okay. Mixed, if you take mixed discussion and conservative and non-conservative, the simpler example you see. This is a body, initially at position A, mass of the body is M, then force, gravitational force is in vertically downward, the body is displaced to a position B through H. And again, it is brought back from B to A. From B to A, then we have to find the work done from A to B, then from B to A. Then let's first find work done from A to B. This position is A. Force is in vertically downward direction, displacement in upward direction. This position is B and displacement is H. So here, theta is equal to 180 degree. Force and displacement are in opposite direction, so work is equal to Fs cos 180. That's equals to minus Fs, means here force is mg, force is mg, displacement is h. And if you take the body again moves from B to A, again displacement is h but in downward direction, and force means gravitational force due to gravity is also in downward direction. Here theta is equal to 0 degree. Both force and displacement are in same direction. Displacement from B to A, force is also in the same direction, in vertically downward direction. So work is equal to Fs cos 0 degree. That's equals to Fs. So F is mg, S is h. This is work from A to B. This is work from B to A. Then total work is equal to work done from A to B minus mgh plus work done from B to A plus mgh. Then total work is 0 because force is conservative. Gravitational force is conservative. So total work in the complete path is 0, A to B, then from B to A. The most simplest example of total work in a complete path is 0. The most simplest. Okay. So in this way, you can do different types of questions. Suppose a force F is equal to, I am changing the expression a little, 3y I cap plus 4x square. Again, if it is asked what is work done in taking a body in a closed path, first from A to B, O to A, then from A to B, then from B to O. Work done from O to A to B, B to O. Then first check this. If this is conservative, then work done is 0. If it is not conservative, then work done is not 0. You will check it because x component of force and y component of force are given. Okay. dy dx of fx, that's equals to dy dx of 3y. So with respect to x, 3 is constant, y is constant. Sorry, this is y, this is y. So this comes 3. dy of y is 1, so this is 3. Similarly, dy dx of fy, dy dx of fy is 4x square. Then bring 4 outside. Bring 4 outside, dy dx of x square is 2x. Then this is 8x. So 3 is not equals to 8x. So force is non-conservative, so work is not 0. Work is not 0, and we can calculate work if the coordinates are given and we have to resolve the force. Okay. Just we have an idea that force is conservative or not, work done will be 0 or not. Okay. In next class, in next lecture, we will discuss a beautiful concept, that is potential energy. Very good concept. The concept of potential energy. Okay. As we have discussed in today's class, conservative force, work done by conservative force defines change in potential energy. Thanks, my children. Thanks.